We'll start with results. All right, so here's round 5, period 5 results. So we're starting to see some trends here. The most obvious one is that look rack at it remains on top. It's proven to be very consistent. Both Tiger, LLC, and Spice Rack have climbed their way to the top, which is great. Racketeers remain consistently strong as well. And Rack City has jumped considerably in the last 2 weeks. On the other hand, you've got Won't Rack Down, who's on the decline, and 30 Rack, who has plummeted, and I say plummeted to the bottom. So that was unfortunate for them. All right, this is sales versus price for period 5. And here is the same graph compared to other periods. So period 5 is the blue dots. And so what you can see here is a trend towards lower prices. Generally speaking, the blue dots are kind of left of the others. And because of competition, the demand is more evenly spread as well. Presumably this has something to do with the fact that several factories became open last period or during period 5. And thus there was a greater supply of goods to sell. This is the plot for this period of sales versus price for each team. Rack City over here, for whatever reason, did not sell many units at all. They set their prices very high. And there were some teams who went pretty low, in the neighborhood 25 to 30. And they sold a fair amount of goods, right? Here's the assets. Again, look rack at it, remains on top. There's 2 teams that are very close for second and third. And then from there, we go down. Stock price. CD's Racks is still maintaining, despite their assets, fairly high stock price, but look rack at it is way above everybody else in stock price. So that probably accounts for a great deal of their success. Well, I think they're playing the market right and they're selling CD racks right too. Here's some results. First, 30 rack is really low in cash. Second, there are some construction projects underway. Third, everybody has finished goods. Everybody. Some teams have a lot of finished goods. So yeah, there's a lot of supply still in inventory, let alone what you're going to be able to make with your new factories. Stock prices range from $23 down to under 18. 30 rack again managed to lose money rather than gain money. We have 2 teams with $2 dividends. And Rack City plans to purchase 5,000 units of their own stock. Again, it's an insider trade that will execute next period. The sales range from 10,000 to 700. You may recall that we said that, 30 rack. Who was it? Rack City. Where's Rack City? I thought maybe I got those mixed up on that graph. This was probably 30 rack, not Rack City. Rack City sold many units. Stock price, okay, and then yeah, sales. So most teams sold 5,000 or more units, and still have leftover goods. So something to think about, I think. All right, are there any questions about the game? So I reviewed it pretty carefully. I didn't see any errors. Didn't see any shady stock market transactions, so everything seems to be going good. So I'm not hearing any questions. So we can move ahead to the lecture. So today's lecture is about game theory. The good news is that I think most people find game theory kind of interesting. The bad news is that of all the topics in this class, this is the one I have the least expertise in. So I'll do my best to tell you what I know about game theory. But this is one field that I'm not well acquainted with, in all honesty. By the way, there are various classes in game theory available at Lehigh. There's a 300 level ISE course and also a 300 level game theory course in the economics department. Both are pretty interesting. So game theory is basically a branch of mathematics aimed at modeling what are called games or competition. People first started thinking about it in the 40s and 50s, in particular. Morgenstern and von Neumann were kind of the pioneers of this field. But I say here it's widely used today in certain circumstances. Widely used might be an exaggeration. It is used in several different applications, most notably in developing auctions and in analyzing negotiation strategies. In particular, like the federal government from time to time will auction off bandwidth in the spectrum, and they use game theory based auctions to auction off that bandwidth. One of the problems with game theory is it gets very complicated very fast. So while you can analyze some fairly simple game situations, it gets hard enough quickly that it becomes impractical or too hard to solve in a lot of real world situations. So you may have seen the movie A Beautiful Mind about John Nash, who won the 1994 Nobel Prize in economics for his work on game theory, in particular about analyzing equilibria, and we'll talk a lot today about Nash equilibria, which is an important part of game theory. So that's a little history. So we're going to start with the simplest type of games. They're called two-person zero-sum games. And so you have two players, and they are adversaries. And so the way the game works is that the net winnings are zero. Basically, player one wins what player two loses. So, right, one will get plus K dollars, the other will get minus K dollars. So there's total conflict between the two players. And there's no incentive at all to cooperate because it's a zero-sum game. So what the game consists of is a set of strategies for each player and a payoff matrix. So here's an example. The evens odds game. We've probably played it to see who gets to go first or something. Each person, you go 1, 2, 3, shoot, and you put down one finger or you put down two fingers. And one player is the odd player, the other player is the even player. So if the fingers add up to an odd number, odd wins. If the fingers add up to an even number, even wins. So here, both the odd player has two strategies, put down one finger or put down two fingers. The even player has two strategies, one finger or two fingers. And when we show the payoffs in a zero-sum game, we show the payoff for the row player. So these are the payoffs for what even gets. If you want to know what the payoff for odd gets, what payoffs odd gets, is just the negative of what even gets. Right? So if both fingers are 1, it's even, and the even player wins. Both fingers are 2, the sum is even, and even player wins. Otherwise, even player loses. And if even wins $1, that means that odd loses $1. Basically, you're playing even odds and betting $1 each time. All right, so there's the strategies in the payoff matrix, and this defines this particular game. All right, in game theory, we assume players are rational. And basically, this means that they want to maximize their expected utility. One of the reasons game theory gets complicated is this whole idea of rationality. So there's a whole lot of fancy mathematics behind what it means mathematically for players to be rational. And getting into that is where I get lost and it gets too hard for me. But in this case of a zero-sum game, both players are choosing their strategies to promote their own welfare. And promoting their own welfare is exactly the same as screwing their opponent, right? So in these games, there's no compassion, no mercy, as they say. And this is how business works, right? So in the business game, you're all trying to maximize your welfare, and usually that will come at the expense of the competition. Now, this is opposed to kind of decision theory, the kinds of problems we've been studying previously, where in decision theory, we're playing against nature or against an unbiased random uncertainty. So we're uncertain about the future. Well, think of the news vendor problem, right? The demand is a random variable. We're not sure what the demand is going to be, but the demand is just a random variable. It's not out to screw us, right? So trying to deal with this kind of random uncertainty in decision theory. In game theory, the uncertainty comes from what your opponent is going to do. And that's a whole different situation. There's a similar kind of game called a constant sum game, where the winnings of both players always adds up to the same number. And these are basically equivalent to zero-sum games. So it's not worth really getting into them, because if you understand zero-sum games, you understand these. All right, so here's a simple example. I'll kind of skim through these. But basically, we have two companies. Each company has 3 strategies. That's strategy 1, strategy 2, strategy 3. And same for player 1 and same for player 2. And then the numbers in the matrix are what player 1 will win. Player 2 will win the negative of that. All right, so here's the game, and we want to decide what strategies one should use. All right. So one way to analyze this is called the maxi-min, mini-max strategy. And so player 1 should select a strategy whose minimum payoff is the largest. And since player 2 wins the negative of what's in the matrix, they select the strategy whose maximum payoff is the smallest. So here's basically how it works. We'll start with the row player, player 1. First, we find the minimum of each row. The minimum is -1, -3, 0. Then we pick the strategy that maximizes the minimum. Okay? Find the minimum of each row, and then find the maximum of the minimums. And that tells us the player 1 should play strategy 3. Right? That's the maxi-min strategy for the row player. Now, what would happen if player 1 picked strategy 1 instead? Thinking, oh, maybe I'll get $3. Well, what would happen there is that player 2 would pick strategy 1 and you'd get screwed, right? Now, if you pick strategy 3, if you're the row player, the worst that can happen to you, and since the other player is out to screw you, the worst that can happen is you'll lose $0 and win $0, and that's why you would play strategy 3. Now, to find out what the column player would do, you do it the same thing except in reverse, because remember that player 2 gets the negative of the numbers in here. So you find the maximum of each column, right? So the maximum of the first column is 0, 3, 2. And then you pick the minimum of those maximums, which is going to be strategy 1, right? And so that that says what should happen in this game. In this game, what should happen is player 1 picks strategy 3, player 2 picks strategy 1. Now, one thing you'll notice about this solution is it's said to be a Nash equilibrium. So you ask yourself, if we're in this combination of strategies, 3 for row and 1 for column, can the row player improve by changing their strategy? So here, if they changed it to strategy 2 or strategy 1, the row player would be worse off. Similarly, can the column player change his or her strategy? Well, remember, they get the negative of these values, so player 2 is worse off if they change their strategy, so this is called a Nash equilibrium. For moving from this pair of strategies, no player can unilaterally improve their winnings by changing their strategy. Okay? So this is a summary of what the two players will choose. And it's an equilibrium solution for the reasons I said. And now, according to the theory of game theory, this is what the players will do, assuming they're rational. Where rationality is defined by all of these fancy math theorems. So this might baffle you a little bit. That's kind of hard to, this is the part that's kind of hard to grasp. Why is it that this is what should happen? Why should this be the outcome in this game? So again, it's tied up in the complexities of rationality. But here's a kind of another way you can show why that would be the solution. And it's based on the concept of dominance, all right? So now we're going to use this idea of dominance here. One strategy dominates another strategy if it's always better no matter what the other player does. Okay? When you go through this, remember that player 1 wants big numbers and player 2 wants small numbers, or more negative numbers, if you will. All right, let's start by comparing these two strategies for the column player. Remember that column gets the negative of these numbers. So you can see that no matter what player 2 does, no matter what player 1 does, player 2 will be better off with strategy 1. Because again, they get the negative of these numbers. So strategy 1 dominates strategy 3. So player 2 will never pick strategy 3. So that is completely stupid for that, so we can eliminate that strategy. All right, so we eliminated strategy 3 for player 2. Now, can we find any other dominant strategies? Well, for the row player, consider these two strategies. We see that player 1 would always pick strategy 3 over strategy 2. Right? So we can eliminate strategy 2 for player 1. Now we continue. Now we see that strategy 1 dominates strategy 2 for player 2. So we can eliminate that strategy. And now 3 dominates 1, and we end up with the exact same solution we found before. All right, so we kind of went through this idea of dominance and showed that this is in fact what should happen, because players can eliminate bad strategies like that if they're rational. Okay, so that is in fact what should happen if players are rational. All right, so here's just another example. The game is different because the payoffs are different. All right, so we'll find the minimum of each row. Here they are, and we find the maximum of those minima. So row player will play strategy 1, find the maximum of each column, and find the smallest maximum. So in this case, both players would pick strategy 1. So again, notice that this is not the highest possible payoff, but since it's a competitive environment, this is what should happen. I find this stuff really interesting. Okay, so this is called a saddle point solution, or equivalently a Nash equilibrium, because neither player can improve their strat by changing their strategy unilaterally. All right, so what about the row player? If row player changes a strategy off of this cell here, row player gets worse. Column player, remember column player is getting the negative of this, so the column player is worse off if he changes columns. So again, it's the saddle point Nash equilibrium solution. And again, that's what would and should happen in this game, assuming rationality. Okay, here is another game. Each player has 3 strategies. Here's the payoff matrix. So is there a Nash equilibrium? Is there a saddle point solution? Are there any dominating solutions? So if we find the minimum of each row, we see they're all equal to each other. And the same when you find the maximum of each column, right? So not all games have saddle point solutions. This one does not. In fact, this is a game that you know. So somebody unmute yourself and tell me what game this is.
Rock, paper, scissors.
Thank you. This is rock, paper, scissors. Or Rochambeau, as it's sometimes called. Even simpler game is the evens odds game we talked about before. Again, the minimum of each row is -1, maximum of each row is 1. And so there's no dominating strategy, there's no saddle point or equilibrium solution. So what do we do in a case like this? So, and when we talk about a pure strategy, so if there was a saddle point solution or Nash equilibrium, that would be a pure strategy. Now, if you had to play evens odds, or for that matter, rock, paper, scissors, in the real world, what might you do? I'm looking at you. What would be something reasonable to do?
After like doing multiple rounds, like you'd play multiple rounds, and then maybe you could figure out a pattern that the other person was doing.
You only get to play once, though. We'll talk about multiple rounds in a minute, by the way. When you play rock, paper, scissors, what do you do? Do you always play rock? How about if you like flipped a coin, made the decision in a random or probabilistic way? That's something you could do, right? In fact, if you play evens odds, suppose you flip the coin to make your decision. All right, then what's your expected winnings and losings? Even if you played multiple times, like Sam suggested, but you flip the coin every time, right? Your expected winnings should be 0. You should win half the time and lose half the time, right? Okay, so that's kind of the idea. Okay, so a randomized strategy, or it's typically called a mixed strategy, is where you place a certain probability, you pick the strategy with the probability. So O1 is a probability. O1 is going to be the probability that the odd player plays one finger, which means that 1 minus O1 will be the probability that the odd player puts down 2 fingers. We'll also define the probability E1 the same for the even player. Okay, so let's figure out the reward for the odd player under the 2 possibilities for what even might do. So if even plays a 1, then if we put down a 1, we're going to lose $1. If we put down a 2, odd will win $1. So this is the expected value of the reward if even plays 1. If even plays 2, then odds expected reward is equal to this, right? So even plays 2. If odd plays a 1, then he wins and gets $1. Otherwise, he loses and loses $1, right? So we just write over here in the right-hand column, what is O's expected reward, right? Now we want to apply our mini-max strategy. We want to, maxi-min strategy. We want to maximize the minimum. So to maximize the minimum of these two numbers, excuse me, I'm going hoarse. What value should we plug in for O1? And the answer is 1/2. Now I just did an example here. I have different values for O1, right? If I try O1 is 0.1, 0.3, 0.5, 0.7, then here are the associated expected values of each one, right? And so we're going to take the maximum, we want to minimize the maximum. In other words, here in this column, the worst we do is 0, whereas in all the other columns, the worst we do is worse than 0. So this tells us that we should pick a 1 or a 2 fingers with probability of 1/2. And then we expect that our expected loss is 0. Okay. You could do the same thing with rock, scissors, paper. So we'll let X1, X2, and X3 be the probabilities of playing rock, paper, scissors. And we're going to actually formulate this in Solver. So I want to go to Solver and show you how this can work. Okay, so I've done this 2 ways, okay? So basically, these are my decision variables and probabilities. I put in some arbitrary ones here. When you pick the probabilities, one constraint is that they have to add up to be equal to 1, all right? Then I computed the expected value for each row, right? It's just 0 times X1 plus 1 times X2 plus minus 2 times X3. So these are the expected values for each row. And then I want to take the minimum of that row. So one way to do this, hold on a second. One way to do this is I'll just put in here the minimum of that row, right? And then I can have a solver model where I maximize the minimum, maximize V, by changing these probabilities under the constraint that they add up to 1. I got to change this back to -1 and +1 as well, all right? So because I've got a minimum in here, my solver model is going to be the nonlinear, GRG nonlinear. So ignore these constraints. Those constraints don't exist except that the probabilities have to add up to 1. And I solve it. And it tells me I should pick rock, paper, scissors with equal probability. Okay, now the formulas for these 3 cells here, the expected value in each column, are given by X2 minus X3 minus X1 plus X3 and X1 minus X2. So if I add a constraint that the objective function value V is less than or equal to all of these, then these constraints guarantee, and since I'm trying to maximize V, these constraints guarantee that I will pick the minimum value in that row. And the probabilities have to add to 1. So basically what I'm doing is I'm reformulating this as a linear program by using this trick to get around having this minimum function, which is nonlinear. Okay, so if I make this my objective function, And I put in those constraints. Now I can solve it as a linear programming model. And of course, I get the same decisions, right? Now, you might say, well, I'm going to play a slightly different rock, scissors, paper. I'm going to change the reward structure around a little bit. That's right. So if column plays rock and row plays scissors, then row loses $2, right, instead of $1. Right? So we could still apply this model. Now it tells us this is the probabilities you should use in this game. Okay, so that's kind of neat. So here what we did is we formulated it to solve the probabilities for the row player. Could have done it kind of sideways and solved it for the column player instead. So these would be our decision variables, etc. And it's solved that way. And you end up with the exact same solution. So I mention this only because for those of you that have taken linear programming class in linear programming, you may recall learning about duality and how each linear programming problem has a dual problem that's equivalent. So in this particular case, this could be your linear program. This is the dual of that problem, and it will give you the exact same solution. So if duality was kind of hard for you to understand when you first took it, this is one way to think about it. There's always kind of a game theory interpretation of duality. Wait, that's not the right one. Come on. What happened? I lost it. Oh, there it is. All right. Okay, so as you might have thought, you would pick rock, paper, scissors, each with equal probability of 1/3. And that's what you should do, and that will minimize your losses. Okay. Now the next topic is non-zero sum games, and they're definitely different, and they're oftentimes a little bit more interesting. Okay, so it's kind of the same. We have two players, and each player has strategies to pick from. But now what we show here in each cell is the first number is what the row player wins, and the second number is what the column player wins. Right? So if these strategies are selected, both players lose 5. So this is probably the most famous game. It's called Prisoner's Dilemma. The idea is that two people are arrested and put in separate interrogation rooms, and they have two choices. They can confess and not confess. So if you confess, but your partner in crime does not confess, then they throw the book at the other guy, and he gets 20 years in jail, and they let you off scot-free. Same if it's the other way around. If row confesses but column doesn't. Now, if both confess, then they're going to have to do some time, right? So they got to both do 5 years. Now, if both stick to their guns and don't confess, then they're going to have to do a minimal time, but not much. They each have to do a year. So that's the payoff matrix for this game. Okay, so non-zero sum games, there's all different kinds of them. Some of them have solutions, or you can tell what will happen. Some don't. Sometimes they're competitive, sometimes they're not. And people often say this is more reminiscent of how most things in the real world work. So they've actually have tournaments of Prisoner's Dilemma, where you write a program to play it, and your program competes against somebody else's program. You program your strategy in, and then you just play over and over and over again, and to see who wins, right? And so, but you have to basically, you're going to program in a strategy. One would be like always defect, in other words, always confess, or always don't confess, or do each one half the time with probability of 50-50. It turns out that the strategy that won this tournament is something called tit for tat. Right? So you cooperate or don't confess on the first move. Then after that, what you do, what your move this period or this round will be whatever the other guy did last round. Right? So if the other guy screwed you by confessing last time, you'll confess the next time. Right? So that's what happened there. Now we're going to talk about Nash equilibria. We already sort of have. For a combination of strategies, if neither player can increase his or her expected payoff by unilaterally changing his or her strategy, we have a Nash equilibrium. So some non-zero sum games have unique Nash equilibria. Some have multiple Nash equilibria. Some of them have no Nash equilibria. So in Prisoner's Dilemma, consider the cell where they both confess. This is a Nash equilibrium. And the reason why it's a Nash equilibrium is because neither player can improve their strategy, can improve their situation by changing strategies. So if the row player changes their strategy, then they're going to go down here and get -20. The column player changes their strategy, they're going to go over here and get -20. So this is a Nash equilibrium. And in fact, it's the only Nash equilibrium in this game. This one is not a Nash equilibrium because the row player, if they change their strategy, they do better. So already that means it's not an equilibrium, but for that matter, same is true for the column player. The column player can improve their position by changing their strategy as well. So the only Nash equilibrium in this game is both confess. Again, assuming rationality, this is what should happen. So this is exactly why district attorneys would offer deals to people to confess, right? As long as the deals you offer have numbers that would make the confess strategy the Nash equilibrium, it should work out for you. All right, this is just showing. All right. So here's another game. This game is sometimes called the Global Thermonuclear War Game. It may sound funny, but it really isn't. Having been fortunate enough to grow up in the Cold War era, you may ask, how the hell did United States and Soviet Union end up with enough nuclear warheads to completely destroy the Earth 20 times? So this particular game is meant to try and capture some of the game theory behind that. So basically, both sides have the option to build another missile or a new missile or maybe a new better missile, or don't build it, okay? So if neither us or them builds the new nuclear weapon, nobody loses anything. It doesn't cost us any money, right? If we both build it, we got to pay a bunch of money to build a new missile, but we're still on even grounds, right? We still have détente. We have mutually assured destruction. But if one country builds and the other country doesn't, then now you're ahead, right? You're ahead of them. Maybe you can dictate terms of some kind of terms to them. So you're better off, and the country that's now at a disadvantage is way worse off. So in a situation like this, what will happen? Well, it turns out that the Nash equilibrium indicates that both countries would have to continue building more missiles. That's the only Nash equilibrium here. And that's how we ended up with enough warheads to blow up the world 20 times. This is called chicken. If you watch the old 50s movies where the guys drive their cars right at each other at high speed to see who the chicken is that swerves out of the way, right? So in this game, if both players swerve, then it's basically a wash, nothing happens. If neither player swerves, well, it's minus 100, or minus your life, basically, minus a whole bunch. And in this case, this player wins $10, or 10 bonus points, if you will. If he doesn't swerve and the other guy swerves, that's because this is really Mad Max. He's super macho. Whereas mildly upset Max only the value to him is only $5 if mildly upset Max doesn't swerve and Mad Max does. All right, so where are the equilibria here? Well, both of these, the blue ones here, these are both Nash equilibria. So this is a case where you have multiple Nash equilibrium, and the problem is now you're not sure what the heck is going to happen, right? So that's a problem. Okay, here's another interesting one. Okay, two companies are considering a big project, a business project. If both countries pursue this big business project, then they both lose $10 billion because they spent a lot on the project and now they're competing with each other and there's not enough demand for both. However, if only one of the countries pursues, then that country gains $1 billion or $100 billion because now they have a monopoly and they're making tons of money. The other country gets nothing. All right? And then the question is going to be, what if the foreign government offers a $15 billion subsidy? So here's the thing without subsidies, right? If both countries develop the new business endeavor, they both lose money. If neither develops it, then nothing changes, it's 0-0. However, if one does and the other doesn't, the one country gains 100 billion and the other country gains nothing. So in this game, the Nash equilibria are these two corner ones, right? And so here, what's going to happen is not clear. Now, suppose the foreign country offers a $15 billion subsidy. So now, in this cell here, instead of losing $10 billion because of the $15 billion subsidy, the foreign company would actually gain $5, right? And here they would gain $115 million. Now, if they don't do the business deal, they don't get the subsidy. So it basically changes this value here, -5, and this value here, 115. So now, if you do that, now what is the Nash equilibrium? Now there's only one Nash equilibrium. And so what the subsidy has done is driven the solution to be here, where the foreign company does develop the project and US company does not because of the subsidy. So that kind of shows you why countries would offer subsidies. So these are just some examples, and they're kind of cool, right? Because you can actually explain behavior by analyzing the games. All right, we'll skip this one. It's just like an exercise. There's only one Nash equilibrium in this game, and it is this one here in the upper left corner. Let's just verify that that's a Nash equilibrium. If the role player changes, they go from 2 to 1, so they're worse off. The column player changes, they go from 2 to 1 or from 2 to 0, so they're not better off, and so that is a Nash equilibrium. You could check all the other ones, but you would find that for all the other solutions, one of the two players at least is better off if they switch. Okay. The next example is sometimes called the Battle of the Sexes. If you click on this link here, there's a nice Wikipedia explanation of Battle of the Sexes and coordination games. So here's how this one works. Couple has agreed to meet in the evening, but cannot remember if they're going to go to the opera or a football game. So the husband would most like to go to the football game. The wife would most like to go to the opera. Both would prefer to go to the same place as their spouse. They can't communicate. Where should they go? Right? So here the woman can pick the opera or the football game. The man can pick the opera or the football game. And here's the payoffs, right? So if they go to opposite places, neither of them is happy. They both get 0. If they both go to the opera, then the woman is happy and the man is more happy, but the woman is happy with 2 bonus points as compared to 1 for the man. Whereas if they both go to the football game, the woman is happy with the value of 1 and the man with the value of 2. Okay? Okay, so what are the Nash equilibria? The Nash equilibria are both go to the opera or both go to a football game. So again, we have this quandary of 2 Nash equilibria. What about mixed strategies? Okay, where you do pick with a probability. So we'll define the following probabilities. The man chooses football with probability P. The woman chooses football with probability Q. Find P and Q so that neither player can improve by raising or lowering their probability. So basically what you do is you figure out the expected value for the man as a function of P and Q, the expected value for the woman as a function of P and Q, and at equilibrium, we know that the derivative with respect to P and with respect to Q should be 0. So the derivative of the man's expected value with respect to P should be 0, and the same for the woman. So you end up by setting them equal to 0 with 2 equations and 2 unknowns. And basically find out that the man should ball game with probability 2/3, and the woman should pick the opera with probability 2/3. And if you do that, note that each person's expected value is 2/3 of a point. Okay, and that is a mixed strategy single equilibrium. You can actually see the plots to see that it's a saddle point. So the interesting thing about this here, note here that at the equilibrium point, each player wins 2/3 of a dollar. Where in both of these cases, opera, football, both players win more than 2/3, right? So that's kind of interesting. Okay, so like I just said, if both couples, if both decide to go to the opera, then they both do better than 2/3. So the reason for that is that they're, in this case, the couples are cooperating, right? In other words, they call themselves up on a cell phone and say, what are we going to do? Well, we're not allowed to cooperate or coordinate in this game. They have to decide their strategy independently and play them. All right, so in these kinds of games, if the players are allowed to communicate and coordinate, they can do better than if they're not allowed to, right? So if you imagine prisoner's dilemma, if you interrogated both of the prisoners in the same room where they were talking, you'd get a much different outcome than if you did by separate them so they can't communicate, right? So here we've been considering games where coordination is not allowed, right? Players have to decide their strategies independently. And sometimes that's the way it is in the real world, sometimes it isn't. Okay, so these 2-person non-constant sum games can have multiple Nash equilibriums in pure strategies. They may have no Nash equilibrium in pure strategies, They may have a single Nash equilibrium in pure strategies. But with mixed strategies, a Nash equilibrium always exists. And how do you find the Nash equilibrium? Just exactly what we did, right? Setting the derivatives equal to 0. All right, now we're going to drastically change directions. Okay, we're going to look at a whole different kind of game. These are called coalition games and involve more than 2 people. All right. So the first thing in these games is, so S is going to represent a subset of the players, or a coalition, right? So you have N players, and you can consider a coalition where some subset of the players go together and form a coalition. And the value function here gives us the value for a particular coalition or subset of the players. Here's a simple example, a land development game. We have 3 players, 1, 2, and 3. Player 1 is a landowner, and player 1 could sell the land for $10,000. Players 2 and 3 are builders or contractors. Player 2 can, if player 2 had access to the land, player 2 could raise the value of the land to $20,000 by building something on it. Of course, player 2 can't build on the land without cooperation from player 1. Okay, player 3 is a better contractor. Player 3 can raise the value to $30,000. All right, so we have 3 players. So there's a whole bunch of different possible coalitions. For completeness, we're going to include the empty set. This is a coalition consisting of only player 2. This is a coalition of only player 3. This is a coalition of both players 2 and player 3. And for all of these coalitions, the value is 0. Because why? You can't do jack without the land. All right? The value of the coalition of only player 1 is worth 10 grand because that's what player 1 can get for the land. All right? The value of the coalition of player 1 and player 2 is 20 grand. Because with those 2 players, you can raise the value to 20,000. So the value of player 1 and 3 alone is 30,000. And the value of players 1, 2, and 3 is also 30,000. I mean, you can include player 2 in here, but it doesn't, you know, intuitively it seems like player 2 is not contributing much, and that would be true, but still the value of this coalition is 30 grand because 1 and 3 are in it. Okay, so these value functions have to obey several things. One is called superadditivity. So the value of a coalition between players A and B has to be greater than their individual values added together, right? So why is this true? Whoops. Well, if it wasn't true, then A and B can fend for themselves and do better. So here's kind of a counterexample. Suppose in our game, instead, the value for player 1 was 6 grand, the value for player 2 was 4 grand by themselves. If you put them together, the value is 9 grand. Well, that doesn't make any sense, right? Because they can each get 6 and 4 equals 10 grand on their own. All right? So the reward vector in these games tells you how much money each player gets. Right? So for example, if players 1, 2, and 3 form a coalition, there's 30 grand total, but we now have to split that 30 grand up among the players, right? So this is how we're going to split up the money. And the solution will tell us what will be the reward vector for each player. And the reward vector has to obey certain characteristics. If you add up the reward that each player gets, x1 plus x2 dot, 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 that has to be equal to the value of that coalition. In other words, all the money is going to get split up. We're not going to flush half of it down the toilet. And there's individual rationality. The amount the player I gets has to be at least as big as the amount that he could get by just sticking to himself, right? So player I will not join the coalition unless there's some benefit to player I. Okay, so any reward vector that obeys these two properties, it's called an imputation. These are just some examples. Okay, so this first one is an imputation because it meets all of the criteria, but this one is not. Okay, here it adds up to 30 grand like it's supposed to. But player 3 is worse off than if player 3 just did nothing and got $0. The third one is not, it has to add up to 30 grand. Okay, this one is an imputation. So is this one, and so is this one. But this one is not because player 1 does worse than if player 1 just went on his own and sold the land for 10 grand. Okay. So basically, any logical solution or reward vector should be an imputation. All right, so how do we come up with a solution? In other words, how much each player gets paid? Well, there's kind of two approaches. The core of the game is more complicated, and then there's a kind of a heuristic method called the Shapley value. So basically, the core is based again on this concept of dominance. So if we have two possible solutions, by which we mean payoff vectors like this, you can sometimes say that one of the payoff vectors is better than the other, and therefore rule out X. Okay? So what happen is there's a particular coalition S, where these two things are true. Okay, so the sum of the yi's is less than or equal to the value of the coalition, less than or equal to, and yi is greater than xi for every player. So here's some examples, right? Here are two imputations. So consider the coalition between player 1 and player 3. All right? So that, and for y, the sum of all the payouts is equal to 30, so that's good. And the same is true for x. However, both players are better off. 15 is better than 10, 15 is better than 10. Both players are better off with the second one. Right? So we can get rid of x because it's dominated by y. Okay, so the members of the coalition X prefer y to x, so we can rule out x. Okay, so the core is the set of all undominated imputations. Okay, here's just another example. I'm trying to get to the bottom line. So basically, you write down what it means to be an imputation and the core theorem. These are all of the constraints that have to be met, right? So X has to get at least 10,000. X2 and X3 have to get at least 0. Has to add up to 30,000. If we look at the two-person coalitions, X1 plus X2 has to be greater than 20. X1 plus X3 has to be greater than 30. X2 plus X3 has to be greater than 0, and they all have to add up to 30. So you take all of those constraints and figure it out, basically. What it tells you is that any vector of this form, so basically, player 1 gets anywhere from 20 to 30 grand. Player 2 gets bupkis, and player 3 gets anywhere from 10 grand to 0 grand. But basically, anything in this range will be in the core of the game and would be a reasonable solution. All right, if you wanted to try and interpret this intuitively, it says that player 3 outbids player 2, but does not pay so much that he cannot make a profit. All right, the next thing is the Shapley value. These equations are complicated. It's easier just to show the idea of how this works. All right, so we'll do an example. The glove game. We have 3 players. Players 1 and 2 have right-handed gloves. Player 3 has a left-handed glove. And so the payoffs for this are basically that as long as you have a right-handed glove and a left-handed glove, the coalition is worth 1. Otherwise, the coalition is worth 0. So the idea is, we say, suppose you had a coalition without player I, and then player I arrives and joins that coalition. How much does the value increase? All right. So this is kind of the way to think about it. We write down all the different sequences of the numbers 1, 2, and 3. All right. And we're going to figure out what is the value that player 1 adds. Right. So when 1 is first, that's like saying player 1 is arriving to the empty set coalition. Right? Whereas down here, player 1 is last. So that means player 1 arrives to a coalition already consisting of players 2 and 3. So here, 1 is arriving to an empty set. So what's the difference between the value of player 1 alone and the empty set? Well, the value of both of those is 0, right? Because if I only have player 1, I can't have a left and a right-handed glove. In this sequence, it's exactly the same. 1 is arriving to an empty coalition, the value is 0. Here, 1 is joining a coalition that has 2 in it already, but 1 and 2 are the players with right-handed gloves. So still, both of these coalitions, 1 and 2 alone, are worth 0. Here, 1 is arriving to a coalition that already has 2 and 3 in it. So the coalition with 2 and 3 is worth 1 because there's a right and left-handed glove. And then the coalition with 1, 2, and 3 is also worth 1 because both gloves. So the difference, so when 1 joins the coalition of 2 and 3, 1 adds nothing. Okay, here 1 is joining 3. So when it's 3 alone, it's worth 0. We only have a left-handed glove. But when 1 and 3 go together, there's a left and a right, and so that's worth 1. And finally, the last one is 0. All right? So basically, you add up all of these rewards and then multiply them by the probability of each of these outcomes. We assume all these outcomes are equally likely. Since there's 6 outcomes, we make it 1/6 times the sum of the rewards. So this tells us we should give player 1 1/6 of a point. By symmetry, we're going to give player 2 1/6 of a point. And because the total money has to add up to 1, we're going to give player 3 4/6 of the money. Right? Player 3 is the only one with left-handed glove. So this would be the Shapley solution value. Shapley, I'm sorry. We kind of guessed at player 3, or we did it by subtraction, but you could do it the same way, right? So player 3 is the one with the single glove. So each of the first 4 would be worth, the difference would be before and after player 3 joins would be 1, and the other 2 0. And so you get 4/6. Okay, we can do the same for the land development game that we did before. Just refreshing your memory as to the value functions. So we're going to find the value for player 1. So let's just pick a couple of them. Okay, here player 1 arrives to an empty set. So the value of 1 alone is 10 grand. The value of the empty set is 0. So player 1 adds 10 grand to this coalition. Let's pick this one here. Player 1 arrives to a coalition currently consisting of player 2. So the value of 1 or 2 together is 20 grand. The value of 2 alone is 0. So we get 20 grand, right? And we do that for all the combinations. We get 1/6 times the sum of the values. And so player 1 should get 130 divided by 6, which is what, 85 divided by 3, whatever it is. All right, we can do the same for x2. I'm kind of doing a shorthand here. But it turns out that 2 is going to get 10/6, and 3 is going to get 40/6. If you do the math, this is the Shapley values, right? So remember, the core of the game was sort of any solution in this range. And so the core of the game said player 2 should get nothing, right? So the Shapley values is more of a heuristic procedure. and it tends to be more generous than the core, right? But in the real world, I think player 2 would be out of luck in this game, right? Okay, so we talked about zero and constant sum games. We talked about non-constant sum games, and we talked about in-person coalition games. That's just a small set of all of the possible kinds of games and situations that are analyzed in game theory. There's plenty of extensions. However, game theory is also very complex, right? So you quickly hit the wall in trying to analyze real world situations because they become too difficult. Okay. So there's a game theory homework posted. Should be not too difficult, I don't think, for a change perhaps. So I think I don't even need to go through it. Although I did add one new problem in the last sentence of the question is, I have no idea how to do this myself, but I think you should start doing this, right? So I'm curious to see what will happen when you do that. Does anybody have any questions? All right. Just out of curiosity, Shayna, Jae Young, and Cindy, are you ghosting me?